Well, I'm Chris Tyson, and I'm the superintendent at the Vidalia Onion Research Center and the area onion agent. I'm the moderator this morning, and you are in the Vidalia Onion session. Well, our first speaker this morning is Dr. Ted McAvoy. He's a vegetable extension specialist in Tifton. He's been doing some plant population and nitrogen studies the last couple years with onions at the Vidalia Onion Research Center. And I'll let him tell you a little bit about what he's found out.
Thank you, Chris. So I'll start off and give credit to my students. These have been student projects. It was initiated by my master's student, Haley, that did plant spacing in multiple crops, and then by my student, Elvis, that did plant spacing with the addition of fertilizer. So the Vidalia onion growers wanted to know, can they increase their yields by increasing their plant spacing? And if they did, how would it affect their bulb size distribution, and would it require extra fertilizer with increasing spacing? So that was what we did. And the reason I say summary is because this was a 2-year study, multi-trials, multiple year. And so these were the treatments. We had a low, a standard, and a high planting density, and then we had a low, the standard, and the high nitrogen rate. And then we had all the combinations. I think if you just press the down arrow, it doesn't turn black. It's not working. It's brighter. There you go. So these were the planting wheels that we used for our planting densities. We had a single row with 6-inch spacing for the 87,000 plants per acre. Excuse me, the 58,000 plants per acre. The middle, we had our mid to 80,000 plants per acre, which was a single row 4 inches apart, so one row closer spacing. And this one on the right was a double row 6 inches apart. So that got our highest population of 116,000 plants per acre, double of the single row at the same spacing. And this is what it looked. So everything had 4 rows per bed, either 4 singles or 4 doubles. And then this was the fertilizer applications. Through the early part of the season, we put out all our pre-plant, and we got all our P and K. And then at the end, we finished up our nitrogen to get our 3 different rates of 80, 100, and 120 pounds per acre, just using cal nitrate. And we used the first product's drop spreader to make the applications. All right, so I'm probably going to milk this study because, I'm just presenting one study. But I'll lead you through a story. So the factors here are year, fertilizer, and density. For year, there was a difference. And of course, environment varies from year to year. But I believe maybe something equally as important, maybe more important, was that there was a poultry litter application on the field during the fallow season on year 2. And I think this brings into the point of real world. So I could make a fertilizer recommendation, but it's going to matter about your soil type, your management practices, your previous crops. So that was different between the years. The first year didn't have poultry litter, and the second year did during the fallow. So 2024 had higher yields, but more unmarketable. So you had more bulbs, more rotten bulbs with that higher fertilizer. The second year, and because of that, because you got more marketable the first year, you got more jumbo and more marketable, and you got more loss and less yield the second year. That was marketable. This is the big take-home message, and I feel very strongly from multiple trials and multiple years that this is good information. For dry weight, marketable, and jumbo, we got higher yields with our high planting density, and this was better than our standard density, and that was better than our low density. The only thing that was in backwards order was the colossal, which is the biggest bulbs, was less at the high density. And this is not a bad thing because jumbo that's the size they really want. So we got more jumbo and more marketable with the higher planting density. I will mention, the first year we didn't see any bolting in the high density. The second year we did, but even though we had some bolting the second year, overall it still yielded more because just seemed like it had a little more stress in those plants, some of the plants bolted. All right, so year by density. So again, this is dry weight, again, before you start sorting them. And I have it planting density in year. So overall, 2024 was higher than 2023. But within year, for the same densities, but then within year, the higher density out-yielded the standard density, which out-yielded the low density. So again, I really feel good about the density trend. The nitrogen was not significant. So as I'll show in a second, 1 year the low nitrogen had the lowest yields, and in a next year the low nitrogen had the highest yields. And I believe that the higher nitrogen had excess of nitrogen with the poultry litter. And that's what I'm showing here. So again, in the first year, you got less marketable with the low rate of nitrogen, whereas your standard and your high were similar. The second year, you got the highest yield with the low nitrogen. So it's the opposite here. And it's just like I explained the reason, my rationale. So either way, I like the standard rate of 100, but I would say it depends on your management practices with the nitrogen. And then this is the big take-home slide. You know, the question was, could we increase yields with density? We could. Would we need more fertilizer? And I believe this answers it reading the tea leaves. So again, all the higher densities are better than the standard and low densities, but within those densities, you can see this higher rate trends higher with higher fertilizer. It's not significant. The standard rate, the highest yield is the standard fertilizer. And then the lowest rate, planting density, the highest yield is the lowest fertilizers. Low density, low fertilizer, standard density, standard fertilizer, high density, high fertilizer. But again, it's not significant, but I think that's kind of the jumbo mumbo that's the bottom line. And that's the end of my presentation. Oh, it's not. That's the end of my data. I still have some pictures. So this is pictures of what it looked like with standard density, or excuse me, low density, one line 6 inches apart. Here's one line 4 inches apart. And you can see here there's really gaps that you're not utilizing with the lower planting density. And then here's your double at 6 inch spacing. And you can see there's, you know, a lot more bulbs. You can see sometimes you might get a big and a small bulb since they're close together. And this was the fertilizer the first year where we saw a reduction in plant growth and yield with the low fertilizer. So this was the 80, and that was the only one that you could pick them out. These are 3 rows here that are smaller and more yellow than in the back. This was 100 and 120. They both looked healthy. And then this is what the bulbs look like on the ground. You can see there's just more bulbs. You're putting more plants out. Each plant makes a bulb, and you have more bulbs with the higher density. You do have more variable size, but again, you're not getting as much colossal. Here you have less bulbs, probably more uniform size, bigger bulbs. So the take-home message was that 116,000, the high rate, had higher yields and more jumbo than the standard rate, and that had more than the low rate. The nitrogen varied depending on management practices and years. In general, I'd say if you didn't apply anything and you had sandy soil, 80 probably would not be sufficient, unless maybe you were doing a low density. But the 100 seemed to hold up pretty consistently, the standard fertilizer rate. And I just want to thank everybody. Thank the Onion Committee for the funding, and Chris for doing the work, and my technician Bob sitting there, and my graduate students. Any questions?
We got plenty of time for questions.
What variety was this?
This was Sweet Magnolia. And that might have played a part about, them getting big and rotten. That's what it seemed like. It seemed like it was the big bulbs that got rotten, and I believe that's why the more fertilizer and less spacing had more rotten bulbs. Yes, Miss Cliff.
You mentioned about the difference between years and maybe some residual fertility poultry litter. So we see this same thing in general terms. Let's just say, let's not talk about poultry litter.
But if you put fertilizer from a spring crop.
That's one option, but it could be something like following peanuts versus corn.
Right.
Whether it is poultry litter or making cotton.
I would probably lower my rate in the fall. Oh.
Would you pull a sample, if you were trying to analyze it, just add this nitrate to the sample?
That's probably a good idea. We didn't pull soil samples, but I believe that would, usually nitrogen, do you get nitrogen on your soil test? Oh, okay. That'd probably be a good option to check, because that's usually the recommendation is they'll tell you P and K and they just say add nitrogen. But I think that would be a good idea to see what you're starting with.
You think adding a nitrate request, or
I'm going to soil man here.
Yeah, if you were going to test nitrogen in the soil, you'd test soil nitrogen. And I mean, I think maybe, your first complete application, maybe you could come back. Because again, like if it's nitrate, it's not going to be there later. Like it's only if you pull off a crop right before, if there's not residual nitrogen, it's going to help you for that first application to complete, but it's not helping you at the end of the, now or, later in the season. So yeah, I mean, maybe you could scale down a little bit on the front end, and your total nitrogen would be lower. But yeah, I would do nitrate from your soils is what so.
Thank you, Daniel. Any other questions? Well, I appreciate it. Thank you.
Thank you, Ted. Well, Daniel, you're already up. Daniel Jackson is going to be our next speaker this morning. And he's going to talk about some stuff he's been doing with soil and flavor work. So I'm going to go ahead and turn it over to him. You want the wireless mic here?
Yeah.
Okay.
Yeah. All right. Good morning, everyone. Thank you for being here. My name is Daniel Jackson. I'm the research coordinator at the UGA Agricultural and Environmental Services Labs. My lab, we study all sorts of things on flavor compounds and quality compounds with fruits and vegetables, but one of the big areas that my research has covered over the last few years is understanding flavor compounds in Vidalia onions. And I'm going to talk a little bit about a project we've been working on the last 2 years, and we're continuing this year for a third year. We're trying to understand how soil variability across the Vidalia onion industry ultimately influences both yield and flavor for the Vidalia onions. So I know you all you're in the Vidalia onion session, so you probably know a lot of this, but just for a recap, Vidalia onions are short day Gran X type yellow onion. They're known for having a characteristically sweet flavor, low pungency compounds. With the passage of a federal marketing order in the late 1980s, production of Vidalia onions is limited to only a 20-county region in southeast Georgia. And with an annual farm gate of about $170 million, it's a significant economic industry in this area of Georgia. But with a brand that's built around having a specific flavor profile, it's really important that we understand the factors that influence flavor for the onion. And so I hope everybody's paying attention because there's going to be a test at the end of this presentation on this. But this is the flavor compound, or this is flavor pathway in onions. And so the green area is basically, this is to represent an onion cell. And so what happens is when you bite into an onion cell or you cut it open, this allanase enzyme that's stored in the onion vacuole interacts with these compounds right here, these alkenyl cysteine sulfoxides. And it just starts this chemical process that ultimately releases a bunch of volatile compounds. And so ultimately what we care about are these compounds that I've highlighted. So the first one down here is this propanethyl S-oxide, is better known as the lacrimatory factor. That's the compound that causes tearing. So when you cut open an onion, it's the compound that interacts with your eyes and causes tearing. It also is responsible for a lot of the burning and upfront pungency in onions when you bite into one. Additionally, the thiosulfonates down here, particularly the methyl thiosulfonates, these compounds are responsible for a lot of the aftertaste and flavor of onions. And so these have like grassy green flavor, metallic flavors, and there's a lot of different compounds. Additionally, another important compound is pyruvic acid. Pyruvic acid doesn't actually have a flavor itself, but it's a byproduct of this chemical reaction, and therefore it's a good indicator of overall onion pungency. And so by measuring these compounds, we can actually determine how pungent an onion is. So when we think about onion pungency, just like any plant response, it's the combination of both genetic and environmental factors. And so genetics in Vidalia, we control this by limiting the varieties. Only specific varieties or onions are able to be grown and called Vidalia onions. However, there's quite a few environmental factors, including irrigation, root zone temperature, nitrogen and sulfur, fertility and availability in the soil, that can influence onion pungency. However, of all of these compounds or factors, sulfur availability within the soil is the most important, because if you remember from the previous slide, all of those compounds that are responsible for onion pungency have sulfur. They're sulfur-containing compounds. So if there's sulfur in the environment, it'll actually result in more pungent onions. And so when we look at sulfur a little bit more specifically, sulfur is an essential element required by all plants for proper growth and development. Too little sulfur causes deficiency symptoms, can reduce yield. Excess sulfur, particularly in onions, results in luxury accumulation. So if it's available, the onions are going to take it up, they're going to store it, they're going to become more pungent. And then some work by Bill Randall in the mid-1990s, and has been repeated many times since then. It's basically shown that if you apply more sulfur in your fertility program, you're going to get more pungent onions. There's a linear relationship with sulfur application rates and onion pungency. And so I was given a few extra minutes with this presentation, so I figured this would be a good opportunity to kind of actually hit some of the basics of plant fertility and plant nutrition. Just backing up some basics, plants require or need 18 different elements for proper growth and development. The biggest molecules or the highest concentrations are carbon, hydrogen, and oxygen. So these are the ones that are responsible for structural portions of the plant. These come in through carbon dioxide, through the stomata on the leaves, or water through the roots. And then all the other elements are derived from the soil. So they're taken up by the roots. You've got your primary macronutrients, N, P, and K. They're macronutrients, so they're at the greatest concentration. Then you have secondary macronutrients, which are needed, but a little less by the plant, calcium, magnesium, and sulfur. And then you have micronutrients. And these are essential, but they don't need them at such a high concentration. And these do a lot of different things from just general plant metabolism. And so when we think about that last slide, a lot of those nutrients are coming from the soil, right? So it's really important that we understand the factors that are influencing soil fertility. And when I say soil fertility, what that means is basically the ability for a soil to supply and retain nutrients to the plant. And so ultimately, this depends on the electrical charges that build up on your soil particles. And so, as soil colloids develop, they create an electrical charge. And particularly, clays and organic matter are the primary things that are driving soil fertility. And if you remember back from like elementary school, you were playing with magnets. You have a positive side, you have a negative side. If you put them together, opposites attract, right? And they stick together. But if you have a negative and a negative, you put them together, they repel each other. So clays and organic matter, they have naturally negative charges on them, which is great because that means they're able to bind positively charged elements. And many of the plant nutrients that we need, you can see are positively charged. And so here you just have a clay molecule or a clay particle, and it's got all the negative charges, and then all of our positively charged plant nutrients are stuck to the outside of that. And so this process is called cation exchange capacity, the ability for the soil to actually hold on to nutrients and supply it to the plant. So this is a really, really important concept. Additionally, and the reason this is so important is because it affects how those nutrients are held within the soil. And so this slide basically is a summary of the elements and then whether or not they're mobile in the soil, what form they get taken up as, and then whether they're an anion, which means they have a negative charge, or a cation, means they have a positive charge. And the take-home message is, in general, anything with a positive charge, so a cation, is going to be immobile. It's going to stay in the soil. It's going to be retained. Anything that has a negative charge is an anion, and it's going to be mobile. So you apply it, it's going to move pretty quickly through the soil. There are a few exceptions. The biggest one being phosphate up here is an anion. It's highly immobile. You apply it, it doesn't really go anywhere because it actually forms a different type of chemical bond instead of that ionic bond. It's a much tighter bond. So there's a couple exceptions to this, but in general, if it's positively charged cation, it's going to stick to those soil particles. And there's a lot of other factors that go into this, but this is a really good rule of thumb. So again, negatively charged nutrients are going to move. And another thing that plays into this is the soil texture and soil type. And this goes back a little bit to Ted's talk previously, is that depending on your soil type and your soil series, it's going to affect how well your nutrients are supplied. And so, if you have a sandy loam soil right here, it only has a capacity to hold, it only has a few of these negative charges. It's going to have a much lower ability to retain nutrients. Whereas if you have a clay type soil, you can see that there's a lot more negative charges on the clay. It's going to be able to hold and retain these positively charged molecules a lot more and supply them to the plant. And so that's why measuring cation exchange capacity is so important, and you can see that there's a big difference between these soil types. So kind of backing up to why this matters, a couple of years ago, we conducted a research project where we took an onion field that was highly variable, and we tried to understand, is there any way, are there any associations with those differences in soil characteristics that influence flavor profile of onions? And what we found is yes, in a Vidalia onion or coastal plain soils, generally you have a loamy sand, that's anywhere from like 8 to 16 inches in a lot of the soils, where it has a topsoil layer, loamy sand, over top of a heavier clay pan. And this can range anywhere from, about 8 inches all the way down to several feet. And what we found is, as you increase this depth to the clay pan, your pungency decreases. And so basically what happens is, if you think back to that last slide, sulfur has a negative charge, so therefore it's not going to be retained on the soil. It's going to move down and bind to this clay layer right here. If onions are able to access those deposits, they're ultimately going to become more pungent. However, if it's a really deep clay pan, all the sulfur that you apply is going to quickly leach down to the clay pan way down here, and they're not going to be accessible for the onion roots to take up. So this is a really important finding. Other really important variables here are soil texture, soil organic matter, and soil pH, because these all play an important role in regulating nutrient retention. So, there's a lot of variability, and so I think it was also important to understand that, there's variability in our soils, but that variability is the result of the factors that were around when that soil was formed. So, the specific characteristics of a soil are the result of the factors where that soil was formed. And so I created this figure, and this is what we call like a landscape position model or a block diagram. You can see these from like the NRCS website as well. But basically what it shows is that there's specific soil types in areas of the landscape. So on a hill summit or the apex or shoulder area, you're going to find Tifton, Cowart soils, things like this that are common, Irvington as well. And these soils generally, I think you guys can see this, they generally have a sandy loam top soil right here that's anywhere between maybe 8 and 16 inches over top of a pretty heavy clay pan. As you move down slope and you get into like a back slope situation here, ultimately what happens is these soils are undergoing a lot more leaching pressure or erosion potential. And so what happens is the depth of the A horizon or this topsoil layer gets deeper. They also start developing what we call an E horizon, which is basically just a really sandy layer that has been completely leached out. So you can see it's actually, a lot of times it's white or it's a lot lighter color area over top of the clay pan. So this gets deeper as you go down slope. Finally, once you get to the toe slope, pretty much all the soils have E horizons. They start getting deeper to the clay pan even more. At this point, we're down in the Stilton to leaf field type soils. And then finally, once you kind of hit a floodplain, you're going to get a soil that looks like this. This is a Pelham soil from a Vidalia field. It's got a lot of E horizons. It's really heavily leached, but it's also undergoing what we call glaying. Basically, what that means is it's sitting in saturated conditions. All the iron in this has been reduced. And so these are really poorly drained soils, but they're also really deep topsoil layers. And so based on what I've already presented, you can imagine that whether you're growing onions on a Tifton soil or a Pelham is going to greatly influence, soil nutrient retention and things like that. So actually now finally getting to the project. The ultimate goal of this was to understand, okay, we know that soils are important for nutrients and flavor in onions. We have a 20-county region in Georgia. What do the soils look like that are actually being used for production? And so the last couple of years we've been characterizing this. Here's just a snapshot of the region, and here's what the variability in soils looks like. So you can see there's a ton of variability. Those are each different soil types. So what we did is in 2023, I went and interviewed 9 different growers, selected 39 different fields that ultimately represented about 1,900 acres. And then from that information, we collected 97 soil samples and onion samples from 13 different fields, and that represented approximately 1,000 acres. And so basically in this field, I forget exactly how big it is, but I think it's 140 acres. We collected 14 points from there. And basically each point was designed to represent 10 acres. And so I looked at the soil survey, identified those, tried to place those points so that we capture the variability that exists in that field, and then went out and collected samples of soil and onions, which I'll talk more about in just a minute. In 2024, did the same thing. 8 growers were interviewed, 35 fields were ultimately identified, totaling 2,500 acres. Ultimately, we collected 117 samples across 17 different fields, and this represented another 1,000 acres in addition to the 1,000 acres the first time, plus an additional 200 acres that were repeated for the first year, so we have a year-to-year comparison. And so each 1,000 acres represents about 10% of the overall industry as far as acreage. So by 2 years, we're over 20% of the industry characterized. And so the way we did this is we went out into the field, we took our GPS, navigated to these points in the field. Once we got to the locations, we harvested the onions from the middle 2 rows within the field. Those bulbs we brought back to the lab where we analyzed foliar nutrients, bulb nutrients. We also measured yield, fresh and dry and marketable yield, and then we're measuring the flavor compounds within the onions as well. Additionally, we characterize the soils at each one of these locations. So as you're going to see in just a second, basically we're augering down. We recreate the soil profile so we can see the depth to each one of the layers, and then we take subsamples from the top 4 inches of each one of those layers to analyze for nutrients, organic matter, texture, and things like that. So we're fully characterizing each one of these locations. And so jumping into some of the results, the first thing that was most evident is that there's a lot of variability. The first one over here, I think you guys can kind of see these a little better than I can. This is kind of standard Tifton soil. This represents a large proportion of the industry. But, so you have your sandy loam over top of a clay pan. And then the next one over here, this one had a topsoil layer of about 1 inch. So there's 2 different locations here where, that's very different. Soils, basically the onions are growing right on top of an eroded clay pan or eroded topsoil. And what's interesting, if you look at this number 80, this number over here is 79. This soil, this is the A horizon. This is that leached E horizon all the way down to over 50 inches. My soil probe bottomed out. We couldn't go any deeper. We never hit a clay pan. The numbers 80 and 79, that's the same field. So 1 inch to over 50 inches in the same field. So it's extremely variable. A lot of other just I think pretty soils, lots of variability within the soils. Then when we look at some of the results, we see a lot of variability in the amount of fertilizer being applied. So we interviewed the growers, asked them how much fertilizer they applied. Some growers applied as little as 26 pounds of sulfur up to 98, and nitrogen 75 to 166 that first year. And same thing for the second year. So large variability between the growers. Yields were highly variable among the different locations. The depth of clay pan, first year 7 to 50, second year 1 to over 50, and pyruvic acid 2.8 to 7.2 and 2.8 to 6.5. And to put that in perspective, a 2.8 pyruvic acid is a really sweet onion. That's something you could basically just pick up and eat. You eat it raw and you're not going to get much tearing. 7.2, that's a fairly pungent onion. That's really not any different than a regular white onion that you would get from the grocery store. So these are meaningful differences as far as pyruvic acid and pungency. So then when we look at the pyruvic acid by onion variety, so the figure on the left is varieties and pyruvic acid concentration. And from 2023, this is from 2024. Basically, what you see is that there's a lot of variability, but there are differences. If you look just at Vidora, which is the last one, and then compare it to a Tanya, for instance, Vidora is consistently milder. It's got lower pyruvic acid, therefore it's going to be a sweeter variety compared to the Tanya. So yes, there's a lot of variability within a variety, but there's definitely a varietal response to pungency. Then when we look at sulfur rate, so 2023 pyruvic acid by sulfur rate. So sulfur rate up here are on the x-axis and y-axis is pyruvic acid. And then 2024, what we see is that there's no response. So I started off talking about how important sulfur was. Clearly, there's more to it than just the amount of sulfur that you're applying across these fields. And so there was no correlation here, no statistical correlation between these. Then when we look at soil type, so just using the USDA soil classification for each location, what you see is, like, for instance, if we look at Tifton, you can have a really sweet onion, you can have a really pungent onion, all grown on a Tifton soil. So there's a lot more going on, and maybe those soil classifications might be outdated. They might not be true because they didn't use modeling to create those in many instances. But we'll talk about this more, there is a general trend as you get these deeper soils. And I forgot to mention, these are in order. Clay pan is shallow to deeper over here. And so what we found is when we look at pyruvic acid by clay pan depth, what we found is it wasn't quite statistically significant the first year, just above the normal 0.05 threshold for our p-value. A little bit of a trend, but it was highly significant our second year. And so again, what this means is as the clay pan depth gets deeper, you're generally getting a more sweet onion, less pungency. When we look at nitrogen rate, I thought this was pretty interesting. The first year, we actually found a strong correlation. More nitrogen resulted in a higher pungency onion. Didn't find that the second year. There was no correlation at all the second year. So that's kind of interesting. Nitrogen and sulfur are related because their sulfur is taken up and stored as an amino acid, so they're related in that sense. But anyway, so what we found is a lot of different correlations. There's a lot of things to try to understand, and to help us do that, the next thing I did was started looking at machine learning algorithms to help decipher all these relationships between these different variables. And so I used a random forest machine learning process to basically identify what are our most important variables. And the first thing it spit out was foliar sulfur concentration, nitrogen fertility rate, bulb size, depth to the clay pan, organic matter, sulfur in the A horizon, and variety. These are my main things. Well, I can't really, once the foliar sulfur concentration is there, I can't really control it. Bulb size, I can't really control. I wanted to see what things are important, so I reran the model, and it spit out the other ones. But basically what it also did is it developed this decision tree. And the first thing it does is it identifies variety, then it splits it out by field. And so what this tells me is there's some other attribute from these fields that I'm not capturing yet. Maybe it's climate, maybe it's soil moisture, something like that. There's something else that I'm not quite capturing. So it's still ongoing, but what I did is for our model validation, we basically take 70% of the data, train a model, and then use the remaining 30% of the data that's just randomly identified to test the model. It performed extremely well. It's a little bit overestimating at the low end of the range and a little underestimating at the high end of the range. But the idea is basically using this statistical model, I can now collect environmental factors, understand the variety of onion growing, and then be able to predict flavor profile in the onions. And so again, this is based on 2 years worth of data. We're in the process of repeating it for a third year. And so I'm actually hoping to model and predict the onion flavor profiles for this year and then see if I can validate and improve my model moving forward. So wrapping up finally, ultimately there's a substantial amount of variability that exists within and among the soils in the Vidalia onion region. There's a large amount of seasonal variability between yield and flavor between the growing seasons. A lot of that's climate driven. Onion pungency appears to be influenced by a lot of different factors, primarily variety, field characteristics like clay pan depth, organic matter, and soil texture, and then nitrogen and sulfur application rate. And then one other consideration that I also wanted to plug, kind of take-home message, is to really think about, whether or not a nutrient is mobile or immobile when you're designing your fertility rates, because so mobile nutrients like nitrate, nitrogen, and sulfate are going to move down with precipitation and irrigation. But another interesting characteristic is, if they move down, they're going to bind on the clay pan. If this topsoil dries out, they're actually going to move back up too with wicking, and as the roots kind of pull, suction and pull the water table up. So that's an interesting factor. If you have a lot of buildup of nitrogen and sulfur in your clay pan, it can actually move back up and supply some nutrients to your plants. And so managing irrigation and fertility should be thought of together. They're intertwined. The way these move are really, really important. And they're all influenced by precipitation, soil texture, and crop maturity. So finally, thank everyone for being here. Thanks to the Vidalia Onion Committee for funding this research, all the people that helped out, the field crew, Guy, Matt, and Michael. It's a ton of work collecting all these samples. It was a lot of fun, but it's a lot of work. Chris, thanks for your help identifying growers and all that. And finally, if you're interested in this project and learning more, I developed a website to summarize all this data, and it's a pretty fun website. But anyway, I'm going to be repeating this for a third year, and so let me know if you have any updates. I don't know how much time are.
You got plenty of time for questions. You got
Okay.
15 minutes.
Oh, wow. Yeah. Are there any questions?
I have a question.
Sure.
So, Daniel, you talked about so many variables that come into play with flavor. And year to year, we see a lot of differences. I know you mentioned that one year the nitrogen rate seemed to influence the flavor.
Yeah.
And then you also showed that, I don't know if it was for 1 year or both years, that the amount of sulfur applied did not come into play.
Yeah.
So I guess the more questions you answer, the more questions, it creates more questions.
Yeah.
So to you, I guess would ask, what do you think are some of these other factors that that may be influencing the flavor? I know you talked about precipitation and soil temperature, but
Yeah.
can you talk a little bit about maybe how you think that may influence the flavor?
Sure. And this goes back, I'm going to use this mic,
Okay.
I guess, now. This goes back to TED's talk, honestly. I think a lot of it comes down to timing, too. So, like, if we're applying nitrate at the end of the season, cal nitrate's generally how we finish out the year. If you're applying that and you get a big rain event right afterwards, it's highly mobile, it's going to move. Maybe you're not getting all of that into the soil. I think timing, precipitation. I know in this last year, 2024 growing season, a couple of our early season applications, we got you plant the onions, you do a complete application. We had a couple really big rains right at that point. When we were going out and installing some moisture sensors, we actually saw a bunch of fertilizer at the bottom of the field that had been washed off. So it's like those nitrogen credits weren't really going towards the plant, but it's included in our model. So I think there's a lot of factors there. poultry litter, residual nutrients are important. I've seen that in previous studies, that we didn't account for legacy nitrogen in the soil or legacy sulfur, and it influenced the pundency and kind of messed up some of the results. I think you're exactly right. The more we answer, the more questions we're having. I do think ultimately we're learning a lot more. The take-home message, I think, is variety is extremely important, and then soil is important, water is important. I think that's something that we probably haven't taken a close enough look at, is understanding how we're irrigating different soils, because there's going to be differences on like nutrient movement and things like that versus a Tifton soil and a leaf field soil or something like that. Yeah.
So based on your work, that you need sulfur and nitrogen to produce onion, yes, but also
Yep.
you don't want to make it so pungent.
Yeah.
So what's your balance point, like, what's the right combination that you're providing enough sulfur and nitrogen, but also not creating a pungent onion?
Yeah, that's a great point, and I think so. Soils are so variable; it's hard to do it from a soil test. I think doing a mid-season foliar testing is the best way to do it, and I think some growers are doing that. But I think you could always, if you're low, you can always come back and spoon feed another nitrogen or sulfur application later in the season if you're thinking you're going to be deficient. So my suggestion would be back off a little bit. Let's monitor with foliar sampling, and UGA has pretty good established ranges for foliar sulfur and nitrogen that, from my visual experience, look like they're doing a pretty good job of telling us where they are. So like if I see a foliar sample that comes in and it's got 0.25 sulfur, I know that's going to be a good yielding crop, but it's also going to have really good pundency. It's got, meaning low pundency, so good flavor profile too. So I think using foliar sampling instead of new soils is probably a little bit more accurate.
You mentioned about the rain and nitrogen leaves. Do you see the value of some of the nitrogen-fixing bacteria that you can apply as products to?
Yeah, I think there's a lot of potentials. I think a lot of it needs to be trialed, and I think it needs to be trialed on different soil types. But I think there's a lot of avenues that could still be addressed. Thinking about organic production, I know poultry litter has some downsides from food safety standpoint, but there's opportunities for, the mineralization over time. It's basically slow release. Instead of just throwing nitrate out that's going to either be taken up or leached out in a week or two. You having some sort of organic process, I think would be helpful. But yeah, decreasing the rate of nitrification and things like that would be another avenue. I don't know. I had that question yesterday. Then how many acres of Vidalia onions are organic produced?
It's probably it's definitely less than 10%, probably less than 5% of the acreage. So our acreage is approximately 10,000 acres. So you're just talking about less than 500 or 1,000 acres total in our industry. Any more questions?
Eric?
When you're doing your statistical analysis, did you look at an interaction between soil type and variety or your ideal flavor?
Yeah, and so that's all in the model and as well. And so like if you notice right here, it doesn't pull soil type specifically, but it pulls depth to clay pan, and it does. Variety is always at the top of the model. So yeah, it's definitely very important, and they're both intertwined.
So would that help you give grower recommendations for if you have a field that's a particular soil type, you would recommend one variety, and then for your other fields a different variety?
Yeah, exactly. Yeah, so like if you looked back at the variety trial or the variety thing, Vidora, if you grow it on a heavy clay pan, like on a Tifton soil, it's probably going to be sweet. But if you grow a Tanya on a heavy clay pan, it has the potential to get more pungent. And so using just this information from this study, I can already say, okay, what soil type do you have? What's your depth of the clay pan? Maybe you want to grow this variety there. It's going to have the better potential for maintaining superior flavor. So,
Great, thank you.
yep. All right.
I have one more, Daniel.
All right.
At the beginning, you talked about, you had a chart that showed like different nutrients, elements, and if they were mobile or immobile.
Yeah.
And I noticed that you had nitrogen on there.
Twice.
Yes. So I'm assuming
Yeah.
the mobile one is nitrate.
Yeah, nitrate's mobile and ammonium is not. Because,
Okay.
and again, looking at so ammonium's got the cation, it's got the plus sign, so it's going to be held on to those negative charges. Nitrate's got the negative charge, so it's highly mobile. And so most of our nitrogen that we apply is nitrate, and there's been a lot of, for onions, there's actually been a fair amount of research done by Tim Coulong and others that show that, onions really do prefer nitrate, even if it is highly mobile, than ammonium. Ammonium, it can take it up, but it's not preferred. You get better yields with nitrate.
Okay.
So, but that interplay, I think, is definitely something that we could continue to look at.
Yeah, that kind of got me thinking, we use a lot of ammonia-based nitrogen in the first half of the season.
Yeah.
And then we finish up with nitrate for typically it's been for, I guess, reasons related to flavor and storability and stuff like that.
Yeah.
But I've never really thought of ammonia as not mobile, but I guess I learned something. So, but anyway, but going forward with that, do you think that using more nitrate at the beginning of the season might have any implications for any benefit for the growers?
I'd want to look back at a lot of Tim's research that he was doing a couple years ago about like the fact that only a small amount of the nitrogen we apply early season is taken up by the crop. There's really low nutrient use efficiency early in the season, and so I think his results said we could back off on our nitrogen rates pretty significantly early in the season because it's basically not sticking around. It's not being taken up by the plant, but the last few applications are really important.
Okay, thank you.
Yep. I think
All right.
Luan's next.
Okay.
I'll get him.
Well, thank you very much, Daniel. We appreciate your talk. That was very, very informative, and glad you got an extra few minutes to answer questions and kind of give us a refresher on some soil science there. So, all right. Yeah, let's give him a round of applause. All right. Our next speaker is Dr. Luan Oliveira. He's going to talk about some precision ag work that he's been doing the last couple of years in the Vidalia area. And he's an assistant professor and precision ag extension specialist with UGA. So, Luan, come on up and share what you have with us.
Appreciate it, sir. Good morning, everyone. Hope my videos are working. I think I tried this morning, but I was just speaking at the Precision Ag session and they did not work. As Chris said, my name is Luan Oliveira. I'm a Precision Ag and assistant professor, and more than that, Precision Ag extension specialist. So all my projects are designed for the growers. And we did have some projects with mechanization and precision ag last year. And thank you, Chris, for that. Thank you, Eric. Let's go. This is my lab. Actually, this is an outdated slide. I have currently 6 members, including me. And as you see, all the backgrounds, they are different. So we work with artificial intelligence, precision ag, like drones, spraying drones, robotics, and some of them are applied to onions. The first project I would like to talk about is the quality of transplanting. So just like a short, long story, I was a county agent in Midwest, so all I know was corn and soybeans. And then I came to become a precision ag specialist for vegetables here in Georgia. And first thing I wanted to work was onions because we liked Vidalia onions since Nebraska or since Alabama when I was living there. And then first time I went to see a Vidalia onion field was during transplanting. And I wanted to know how much time it takes because we wanted to implement mechanization. Everything is done by hand right now. If you're a grower, you know, right? And we found like pretty interesting results on that. Like the first thing is that for an average field work, and this is a study that we did in 23, we repeated this year in 24. So for an average field worker, it takes more or less 26 hours for one person to transplant 1 acre, okay? 5 foot bed, 6 foot, yeah, 6 foot bed, yeah, 4 rows, that person is gonna take 26 hours. And that's the average of these 25 field workers that we measured in 2023. But if you're looking only at the 10 fastest people in that field, it takes about 20 hours for them. But if we're thinking about talking about the slowest people, it's gonna take 34 hours for them to transplant that field. And the reason I'm doing that is I want to compare that those field workers, like the hand transplanting model, with a mechanical transplanter. And then we repeated that trial in 2024, like late last year, with 70 people. So right now we have a more robust data set to tell. And this year, actually, an average person was 26 hours last year. Right now it was 22 hours inside of that data set. The fastest person, instead of 20, it was 17 hours. And then the slowest person, 27 hours more or less instead of 34. So those guys, it was a different field, it was a different crew, right? So they transplant differently. And this is, yeah, more or less, yeah. That population is a little bit higher, I believe, Chris, and it's between like 99,000 and 100,000 seedlings per acre. So yeah, so that person is just transplanting that bunch of transplants in 27 hours. It's a lot. On your knees, doing all that work is a lot. And the way we measure this, in the first year, I was there like looking for them, and I kind of realized that they were kind of doing better when I was steering there, looking at them. So this year we did in a distance. So we flagged the field 15 feet, and then when the worker was crossing that horizon, we start the clock, and then when he crosses the other flag, we stop it. So that's based on 15 feet transplant, and then we extrapolated that data to acre. And the reason Chris, I think it's this one here. Yeah, right there, so you can see it better. The reason why also we want to test machines in the field is because of that. So you have 100 people working in that field. Those 100 people, 70 to 100 people, they're going to be planting differently. Some of them better, some of them not so better. So what we found is in the fields, we are finding a lot of what we call laying on the ground seedlings. They're just dropped there, For you to plant fast, and then I came back to Chris, I came back to Daniel, I said, hey, I'm finding this in the fields. Is this normal? And the answer was, yes, this is normal, but those onions are going to make it. And then thinking about the physiological stage of those onions, if one onion is really well transplanted like that one, and this one was not really well transplanted, this one for sure is not going to produce the same. So we put a study on the ground, and this year, just to show this data here, this year we did a study on the quality of those fast guys. Like for example, we were measuring the person and seeing how much plants were left on the ground after that person transplanted, and how many plants were double transplanted, and how many transplants were just, we call it partially transplanted. So that person put the onion inside of the hole, but didn't close it. And what this graph, is really busy, but what this graph basically says is not significant, like we didn't have a good fit, but we have trends like there. So the data is decreasing right here. And this is the number of plants laying on the ground, the number of multiples, and the number of plants partially transplanted. What we saw is that as the slower that person was transplanting, the better was the quality. The lower was the number of laying on the ground, partially transplanted, and multiples. As you can see right there, those are the trends. In between like 15 and 20 hours to transplant, 20 to 25, 25 to 30, and then it varies by field worker. As you see here, this is number of transplants laying on the ground. No, this is population, I'm sorry. So the population varies. This is in 15 feet right there, 122, 139, 140, 140. So sometimes people are gonna plant more or less as well. They need to be really quick on that transplanting to make that money, right? Some of them are paid by hour, but some of them are paid by the food. So, and then right there, number of, the percentage of those plants laying on the ground. This is 2023. We found that those workers 1 and 2, that was about like 11%. 11% of 100,000 is 100,000 seedlings, right? 11,000 seedlings. So 4%, 8%, and this is 2023. This is 2024. We saw statistical differences in between morning, afternoon, and late afternoon as well. So in the late afternoon, population was lower, significantly lower than the afternoon time. Also, the plants laying on the ground, it was in late afternoon, it was higher, that number. So these are like really preliminary, but you're gonna see these results. And then we wanted to see how that goes. Like if we put those situations in a controlled environment, in a replicated trial, how much are we losing? So we had those treatments. You saw those plants just laying on the ground, partially transplanted, a control, which means that those transplants were like actually placed really well inside of the holes. Multiples, 25% multiples, and 100% laying on the ground. So here, just a video of us transplanting for you to see. That's a plant just laying on the ground, and my graduate student, he's like doing the control treatment there, which like the plants are really well transplanted. You see, laying on the ground, laying on the ground. So we had those treatments, 25% laying on the ground, 25% partially transplanted. Control, and then we measure these variables: number of leaves per plant, population, yield, and the classification afterwards. Okay, mortality. The control, where we transplanted really well, and this is 30 days after transplanting, gave us the population on the target. We wanted to plant this, 113 plants inside of that plot, okay? Multiples, of course, we had more, we had over, but the treatments on 25% laying on the ground, about 20 of those plants died inside of that plot. So, which means that, you know, more or less, all of the plants that we just left laying on the ground died. I was talking to Dan, he's back there, I was showing the results, and he said, come on, those plants still make it? Because we had like, in the 100% laying on the ground treatment, we still had a good population there. But population doesn't mean we have production, right? So average number of leaves per plant, which is highly correlated to yield. The control treatment, you know, like well transplanted was better, about like statistically different from all the other treatments. And here's the yield. So the properly transplanted yielded about 10,000 pounds more than when we had 25% of those transplants laying on the ground. This is pounds per acre. And if you think about 100% laying on the ground, that's where Dan said you can still get yield out of that. So it was pretty bad. So we kind of proof concepted that if you have, if the plants are properly transplanted, you can have more production in comparison with the plants that are just laying on the ground. And our data says that we have at least 10% of those in commercial fields today, depending on if your crews are being paid by the hour or if they're being paid by the food. So, and that gets it gets even worse because we graded those onions, and as you see here, on the 25% laying on the ground, we got only about like 83% of jumbos compared to the 88% of properly transplanted onions, and then those laying on the ground also gave a high percentage of small bulbs, like really small. I wanted to get them. Chris wanted to throw them away. I said, no, I want to bring them back to the lab and measure them with the caliper to see how big they are. So it was about 11% of small bulbs, like really small. And then, like as a take-home messages, there's a large variation in transplanting quality between those workers. The issue is that like partially transplanted doubles in laying on the ground. The properly transplanted transplants have better growth and generate more jumbo bulbs along with more yield. And then we have another ongoing. I'm going to go really quick. Do you have time, Chris? So, that's good then. So that's why we wanted to implement a mechanical transplanter trial. And we did that this year. So you saw here the first type of transplanter that we were using. And thanks Mechanical Transplanter Company for bringing the equipment here. This is a carousel transplanter. This is made for plug root onions. This is not meant to be used by bare root onions, okay? Because there's a large variation in size of those seedlings after they come from the seedling beds. And what I can tell right now is that it doesn't work really good for onions. But then we found another solution. There's this pocket transplanter. And as soon as I arrived, I talked to my growers as well. I said, hey, why don't you use those transplanters? And they said, it's too slow, Luan. I cannot use it. It's too slow. And then I said, how slow? Like, are we comparing to those to the crews, to the field workers? And they said that they did that in the past, but I said, let me do it again just to double check like how that goes. So as I brought here, like those transplants, it's fixed. A 4-row transplant with four guys there, like placing the seedlings inside of those pockets. If we're talking about 0. I'm just going to bring this data here as well. If we're talking about transplanting 1 acre at 0.30 miles an hour, that's really fast. We cannot keep up. I tried. My students tried. It's impossible to move with the equipment. It's too fast. But 0.20 miles an hour, which is going to take more or less 7 hours for you to do 1 acre, is doable. But it requires training. At 0.15 miles an hour, it takes 9 hours to transplant 1 acre with that machine. That one, each one of those, like even the carousel or the pocket finger transplanter, okay? It takes more or less 0.15 miles an hour to transplant at 0.15 miles an hour, it takes 9 hours to transplant 1 acre more or less. If we compare with the field workers, how much time they're taking, and you have in bold here, so it takes 5 hours for four fastest people in that field to transplant 1 acre, which is 4 hours less in efficiency than the slowest speed at the mechanical transplanter. But if we're thinking about the average, is only 2 hours, and if you're considering only slow people, is the same, 9 hours to transplant 1 acre. In 2024, the workers were a little bit faster, so the average, 6 hours is going to be 3 hours less. But what our results are showing is that, yes, you're losing efficiency, but you're gaining in quality. Everything, all the outputs that is being placed on the ground here, they are being placed in the same depth, they're placed in the same spacing. Of course, with the pegging wheel, you always have the same spacing as well. But right there, you're being planted in the same depth and not leaving doubles, triples, or plants laying on the ground or partially transplanted. That's the take-home message for this study. And we are also doing some yield prediction trial studies. So this is a drone trial we did last year. We're going to repeat this year again. Thanks GNR Farms and Ashley Days for giving us the fields and the onions for us to try that. As Daniel was showing, he was doing some modeling for predicting sweetness, right, Daniel, according to the soil type. And here what we did, we flew the drone every other week during 3 months, just capturing the images to see if that's possible for us to predict the yield just using the drone images. And what we found is that at 30 days before harvesting, we could predict the yield with 73% accuracy. That's the first year of data collection, really preliminary. This year we're going to repeat it again and see if we can improve that, because that's 30 days before harvesting. If every year, 30 days before harvesting, we could fly a drone and know how much we're going to produce, that's going to be really good for the marketing team, I assume. Okay, as the onion prediction, and those are like yield maps from that field, so we can catch up the variability on the size of the onions as well inside of those areas. And this is onion side estimation with the drone. This is not us developing anything. This is a commercial platform. Right there, I'm going to play this video really quick. This is a drone picture from the Vidalia station. And after I zoom in, you're going to understand what we're trying to do. So those are onions from a drone image after harvesting. So they're just laying there curing. We flew the drone. We wanted to know if we can count those just using this commercial platform, which is called Sulfur right there. I did not collect any data to ground truth the model. The only thing I have is visual right now, but we're going to repeat this trial this year. And then when I clicked that button, the AI counted all the onions that are inside of that field. And it also measured. So I don't know how accurate that measurement is. We have still some gaps, some onions not being identified. But this is like really preliminary, really new for us as well. And we're going to be doing this trial this year. And that's it. Thank you. Appreciate it. If you have any questions, please let me know. Thank you, Chris.
Are there any questions for Luan? Any questions?
So the transplanter, it's just doing one row. I mean, obviously, you talked about efficiency. I don't think you didn't mention the fact that you also have to have someone in the tractor driving the tractor. But if I know a lot of other planters will do like three rows at a time instead of just doing one or something like that. So could that same planter be retrofitted? So instead of just doing one with 4 people, if you could do 3 rows, like if it folded out and did 3 rows, and instead of 4 people per row, if you could do, your average of 8 people total for 3 rows, you're going to greatly increase your efficiency really quickly.
Yeah, there are some models on the market, but as I told you, on the population we're doing, for those people to keep up with transplanting is really hard right
Okay.
There are some automated models, but we didn't try those yet. They're out of Japan. I've seen them on YouTube.
Yeah.
There's another transplanter from India that I'm trying to bring it here. I'm open to any model that I can come and compare and see if we can improve not only the efficiency, but the quality of that transplanting. Because my concern right now is that I'm going to get together with Greg Thompson and say, hey, how slow I can go to, like, in comparison to this quality, to increase the quality, you know?
Yeah.
Because like, my concern right now is the quality that has been transplanted in those fields. And if you think about like those 25% laying on the ground, we lost 10,000 pounds. What we're seeing in the fields is about 10% laying on the ground. So we're talking about 5,000 pounds per acre.
Yeah.
So, right now it's not efficiency, it's more like quality what we're trying to measure. For next year, if we have more materials, more transplanters to try, we're going to for sure implement that in the trial.
Okay. Yeah, and also like so, I mean, when the guys are taking them and they're putting them in, were they in the bundles like rubber bands? So like they're like basically like the normal transplant right now, you take the transplant, you put a rubber band around it. They have to like take the rubber band off, and like it's hard to get the roots. They're like intertwined. It's hard to like pull them apart. And so like I don't know if there's a better way to like store the onions between seed bed and transplanting that'll like make it more efficient.
With like from the trays, and it was even worse. Like, because the volume was too much because the population is too high.
Yeah.
And we cannot keep up with that. It was even worse than the bare root transplants.
I want to make a comment, not really a question, but I would say I was a little skeptical at first about your trial with the plants laid on the ground, because we see a lot of growers do that, and those plants most of the time they survive, but you really put the numbers to it, and we can see the losses. And you've repeated that trial, right, this year? Yeah. Yeah. Because I took a look at it the other day, and when you have good weather, you probably get a lot better survival. But we've had a lot of freezing cold weather that's not good for onion growth, really, for a good portion of the transplanting time. So I'm kind of looking forward to this year's results for your second year, because I anticipate you probably won't have as good a survival that you had in the first year, so it makes it even more important, to do a good job. Yeah.
The weather was good. Yep.
Yeah.
We got those results with that weather. Yep.
Any more questions?
Yeah, Luan, what's your
All right. Any more questions? All right. Well, thank you, Luan.
Thank you. Appreciate it, guys.
All right. Last but not least, we've got Dr. Dutta, our plant pathologist. He's going to come talk about progress in onion disease management. You want the cordless mic?
Yep.
Okay. So I can pull up your slide there.
Do you have the
It's
pointer?
right here.
All right. Thank you, Chris. So I am 4 minutes earlier than my schedule, but I'll take it. How's everybody doing today morning? So before he pulls up my presentation, I'm going to tell you that all the research or the outcomes which I'm going to show today has been either funded by Vidalia Onion Committee or USDA NIFA or other federal agencies. So I thank all the commodity, state, as well as national funding agencies for supporting our research. When I started my program, I have been told that, hey, onion diseases are very, very important. You have most of the program you have to focus on onion diseases. Then I looked at number of diseases it can get. I saw that the Vidalia onion can get at least 24 diseases. Okay, out of those 24, 7 diseases occur every year. Out of those 7, 5 are bacterial diseases. So that's my majority of my program on onion. I focus on bacterial diseases, but some of the fungal diseases and Oomycete diseases I'll be talking today that include botrytis leaf blight, that includes stemphyllium. Those are 2 major fungal diseases, and another disease which I'll be spending few moments is onion downy mildew. So the onion downy mildew is Oomycete disease. It's a sporadic pathogen we do not see every year, but when it occurs, and if you are unguarded, not up to your fungicide program, then it can cause a huge loss. So if I remember, there are certain years, I think in 2012 and 2014, we had, particularly 2012, we did not have enough fungicide tools for onion downy mildew. We lost a lot of our onion crops, and it appeared right 2, 3, I think 4 weeks before harvest, and it made a lot of damage. That initiated a lot of onion downy mildew research. But again, when you do onion downy mildew research, you don't see downy mildew every other year. I keep doing research irrespective if it appears or not. But when it appears, our county agents and myself, we do our due diligence and collect enough data. But anyway, that's the background. So what you're seeing here, healthy Vidalia onion. This is how it looks, so pretty. Okay, this is a bacterial disease on onion that appears right now around January and February. It's called Pseudomonas, caused by Pseudomonas viridiflava, Pseudomonas allivorans. It's known as bacterial streak and bulb rot, and this is a post-harvest disease. Sometimes we see this disease before harvest. It's called sour skin. So I'll start with the onion fungal diseases. So botrytis leaf blight is an endemic to Georgia. We see this particular pathogen, particular disease every year. This disease is caused by botrytis squamosa. And in 2024, this disease was widespread, but we do have moderate level of severity of this disease. The pathogen is characterized by these ghost spots on the foliage. And the bad thing with the disease is that if the botrytis go unmanaged, if you do not do a due diligence in managing this disease, it will be followed by stemphyllium. So what we have seen when we try to isolate botrytis later in the season, we get a lot of stemphyllium because stemphyllium colonizes botrytis spots. Okay, so managing this disease will also be invariably managing our stemphyllium. That's what I wanted to express here. So when we looked at the efficacy of all the products, efficacy of all single products against botrytis, there are 2 important things we found. Rovrel, this chemistry has been there for 20 years, and it's still, we do not see any resistance in botrytis against this particular chemistry. It does a decent job. Most of our growers, particularly in January and February, rely on Rovrel and Pristine and Bravo rotation. So this is still effective against botrytis. Then we have Luna Flex, Omegas, and Mirvis Prime, and LSs. They do a decent job in reducing botrytis. But things that do not work have stopped working. Scala, we have Scala, since 2020, Scala has stopped working. Scala is a group 9 fungicide. It used to be a very good fungicide on botrytis and stemphyllium. Now we have a complete resistance to Scala in botrytis. Marivon, so last 2 years, we have seen a resistance in botrytis against Marivon. Marivon have stopped working. Luckily, our growers do not rely a lot on Marivon. They rely on those other premixes. That's great, but we have a resistance to Marivon. One comment, our growers relied on Luna Tranquility, and Luna Tranquility, our traditional premix fungicide against stemphyllium and botrytis, particularly on stemphyllium. But what I'm recommending, in Luna Tranquility, the tranquility part is actually Scala. Now what we have here, we have a resistance to Scala. So if we put Luna Tranquility on onion plants, we'll put undue pressure on Luna itself to mutate, for the pathogen to mutate against Luna. So we do not want that. That's why last couple of years, we've been recommending to go with Luna Flex, which is Luna, not Scala, rather than it's a difenoconazole. It's a group 3 fungicide. This is non-scalar. So instead of Luna Tranquility, we are recommending Luna Flex. It has the same level of efficacy as Luna Tranquility, but it will do a great job in reducing undue pressure on the fungus to mutate against Luna. All right, these are the ranking of fungicides in terms of stem phylum. The things that work are Luna Flex, Inspire Super, and Merivis Prime. They are moderate. I do not rank them excellent, but they do a decent job, not a great job. But you have to use it in rotation. In between, you can also use Bravo, but these are the 2 and 3 stronger products. The products that has a moderate to low efficacy is Pristine and Quadristop. If you have a stem phylum, I would not spray Pristine. Okay, Pristine, we always recommend Pristine in during early phase of growth, for example, January and February. And stem phylum, we always see around mid-March to late March until harvest. So Pristine and Quadristop, I would not rely on during that period. So we start with Pristine and Quadristop in January and February, and then we move to these heavy hitters. The things that do not work are these. Merivon, we already have a resistance to Merivon in botrytis as well as in stem phylum. Rovrol will not work on stem phylum. Rather than Rovrol will work on botrytis. Omega doesn't have any efficacy on stem phylum. And Scala, again, no efficacy on stem phylum. So these are the important pointers. All right, let's talk about our nemesis, downy mildew. So downy mildew, the pathogen, the disease is caused by a pathogen, and the name is Pernospora destructor. There is a reason they named this pathogen destructor. It destroys the plant if it occurs. If the crop is unmanaged, you will see a complete destruction of plant. What it will do, it will appear. This will be the day 2 or day 3 of the appearance of the symptom. Within 5 days, it can decimate the entire plant. And you have just 5 days, 5 to 7 days. And if it's cloudy, overcast, and the conditions what we have now, it's going to decimate in 3 days or sooner. So that destructive this pathogen is. In terms of fungicides, there are not many great fungicides, hands down, against this pathogen. Some of the fungicides work moderately, but they need to be applied in a certain way and in a shorter time span and within a shorter duration. So we look at the efficacy of individual fungicides. We have Ridumil Gold Copper, Reason, Ridumil Gold Copper and Nordox in a program. We have Orondis Ultra, Nordox alone, Omega, and so forth. So to make a long story short, Ridumil Gold Copper did great. Reason used to be our traditional downy fungicide. It still has some life left in it. Ridumil Gold Copper and Nordox did not do great. I think heavy lifting is still done by the Ridumil Gold Copper rather than Nordox, because Nordox by itself is not good on downy mildew. Orondis Ultra is pretty decent on downy mildew and Omega. So we do have 3 important fungicides that work decent. One is Orondis Ultra, second is Ridumil Gold Copper, and third is Omega. And fourth, I have not listed it here. This is a 2024 trial, but in other year trials, we have seen Zampro to have moderate level of efficacy. So this is the ranking of all the downy fungicide based on last 4 or 5 years of research. As you can see, none of them are excellent, but they do have moderate level of efficacy. For example, Omega, Ridumil Gold Copper, Orondis Ultra, and Zampro. They have moderate level of efficacy. Followed by Bravo and Reason. They have moderate to low. So there is a way we can use Bravo. We can use Bravo with these heavy fungicides as a tank mix or in rotation. But since the duration of the infection is so short, we recommend to use it as a tank mix partner. Phosphite, although I say low efficacy, but phosphite do have its own role in downy mildew. Phosphite is a highly systemic fungicide and is moderately effective against a variety of downy mildew. What we recommend, if you want to use phosphite, use it as a tank mix too. Okay, this is a program for our growers, what they should do. When in Vidalia and in regions for the last 5-6 years, what we have seen a common trend, downy mildew in Georgia appears around 3rd week of February. It has been a trend. After 3rd week or 4th week, that's the time when we see downy mildew in Vidalia. So what we are suggesting, recommending, rely on Bravo and phosphite from January and February. Do something, put something on your plant that will have some systemic and some protectant. So what we are saying, Bravo and phosphite. Bravo is a protectant, will cover the crop. from the outside, and phosphide is systemic. It's from inside the plant. Inside the plant, these guys will provide some level of protection until the pathogen appears. If pathogen appears, then you have to move. You have to rely on some of the heavy hitters like redeemable gold, copper, omega, or on this ultra Zampro, and you can use Bravo and phosphide in rotation or as a tank mix. So this is the program we are heavily suggesting our growers to think about on downy mildew, for onion downy mildew. Any questions on downy mildew or stem phyllium or botrytis before I move on? Yes.
So, the Rudimil Gold, or Rudimil Bravo, Rudimil Copper that you found worked, it had really not been on our recommendation list until recently. So as far as using that, I mean, what's your recommendation for using that as far as frequency and, tank mixing it with anything else?
So again, I will revert back to my comment that the window of opportunity for this particular disease is very, very less. You have just a week or just 2 weeks to 3 weeks to do everything. So what I recommend, if you see a disease, then your frequency of application of these fungicides either will be 5 to 7 days. Sometimes it's going to be 3 to 5 days, because within 2 weeks you should be able to put at least 3 applications, and you still be within the limit of your usage. So what I recommend, if you see a disease, go with the redeemable gold copper tank. You may or may not want to tank mix with the Bravo. Just go alone, but come back after 3 to 5 days, depending on amount of infection, with Orondis Ultra, but tank mix it with Bravo. Okay. Then one more application after 3 to 5 days with the Zampro, and then Zampro or Omega. Omega is also pretty effective. Omega also have anti-sporulent activity, so it will reduce some of the sporulation and reduce some of the infection. But again, you have 2 weeks window to do whatever you want. And these are the products which you can use in rotation. If disease appear on late February, we have 6 weeks till harvest. But if the weather, if Mother Nature can't help us, if there's no rain or it's no overcasting conditions, then the progress of the disease will be a little slower than if it's overcasting. So then you can decide on strength and lengthening, longer frequency of application of these products. So this is what we recommend. Okay. All right, let's move to bacterial diseases. So when we did a survey, there's a national survey done as a part of USDA NIFA, and what we found, most of the onion diseases or onion losses, close to 5 to 8% of the losses, are contributed by a variety of bacterial pathogens. So there are at least 21 different pathogens, bacterial pathogens that can infect onions, and all those 21 are present in Georgia. Out of those 21, there's 7 to 8 are of frequent occurrence, and some of the examples I'm going to show you today. One of them, particularly in January and February, we'll start with these Pseudomonas cornifications and Pseudomonas vidiflava. Pseudomonas cornifications causes yellow bud disease. You can see complete yellowing of the plant. The good thing about this disease, and a good or bad thing, is that this is highly temperature dependent. It loves temperature below around 40 to 50 degree Fahrenheit, okay, like what we have right now. But if the temperature increases, we have seen reverse that symptoms will go away. It doesn't cause a huge damage to your crop, but if it appears and if it's unmanaged, then it may cause some level of damage. But over the years, we have seen not a huge damage with this particular disease. The second disease is bacillus streak and bulb rot. It's caused by Pseudomonas vidiflava. That's a traditional pathogen, but recently we have found that some of these strains are actually Pseudomonas allivorans. So it's a new pathogen. So this particular pathogen can cause a bacillus streak and bulb rot. Luckily, we do have a very good management of this particular pathogen. We can manage this pathogen with the use of copper and manzate. We can manage this pathogen with the use of your optimum nitrogen fertility and so forth. And some of the varieties which we use in our Vidalia region have some level of resistance against this pathogen. Okay, the important pathogen which we see and can cause a the problem in onions is is a pentose species complex. This particular pathogen species complex can cause center rot. Center rot, as the disease suggests, it will cause the rotting of the central leaf, and as the pathogen progresses, or the disease progresses, pathogen can invade from the central leaf to the bulb. If it gets into the bulb, you'll have this internal bulb rot. Okay, so while grading, even if you harvested onions, they look healthy from outside, but when we cut open, you will see the center rot. So, all right, when we hit the late season, around early April, mid-April, we are close to harvest or we are already harvesting, we'll start seeing sour skin. Sour skin caused by Burkholderia cepacia is a warm weather-loving pathogen. During April in Georgia, what's the average temperature? We get around 80 degrees Fahrenheit. And this pathogen loves any temperature above 70 degrees Fahrenheit. Then we'll also see some of the rotters like onion bulb decay caused by Enterobacter cloacae, and we have also slippery skin. Slippery skin is rare. We don't see a lot of slippery skin, but we see a lot of sour skin. So basically, we deal with two very important bacterial pathogens. One around March and April, it's a center rot, and another is sour skin around April and onwards, and also in post-harvest. All right, I'm going to tell you a little bit of story, a little bit of thing which we have done, a survey which we have done. I think Dr. Kefas Fande, my postdoc, along with Dr. Daniel Jackson, who just presented, they have done a survey of the Vidalia region. They wanted to see what is the prevalence of Burkholderia and Burkholderia different species complex in the entire Vidalia region. So they did a survey. The survey included 120 samples that represent close to 1,200 acres of the Vidalia. So these are the composite samples which we're looking at. And what Dr. Fande did, he tried to isolate the Burkholderia on these specific plates, and he was able to isolate Burkholderia from 100% of the samples. So all of these soils had Burkholderia. But what does it relate to onion diseases or onion bulb rot? We will see, I'll tell you. Okay, here what you're seeing, all the different Burkholderia species. You see Biferia, Arboris, Cepacia, contaminants, blah, blah, blah. A lot of these. But out of these, what is the most common thing which you're seeing here? This green and blue bar. This green and blue bar are sour skin causing Burkholderias. They are present in most of the soils. Okay? And what we are showing here is the amplicon sink. It's going to tell you what are the distribution of the different or abundance of different Burkholderia species you have present in the soil. And what we found, although do have some level of diversity of different Burkholderia species and their abundance, but one thing is common is all of them got a Burkholderia cepacia or Cepacia. Now, what it relates to the disease. So out of 120 samples we collected, we also harvested onions from those 120 sites and stored them and looked for Burkholderia infection, sour skin infection. So we found different level of sour skins. Not all field sites had onions with sour skin, despite they have Burkholderia. So what does it mean? It means we do have Burkholderia, but not all Burkholderia are onion rotters. Okay. Later on, based on research by our bacteriologist in Athens, he mentioned and he found that for Burkholderia cepacia to be pathogenic onion, you need to have a sulfur-containing gene cluster. Okay, if you don't have a sulfur-containing gene cluster and you are Burkholderia cepacia, you'll not be able to rot the onions. That's why you're seeing, despite the presence of Burkholderia cepacia in all the samples, not all of them were able to rot the onions. Okay, for example, in this side, you can see close to 20% rot, where here, they do have Burkholderia cepacia, a good bit, maybe more than these, but they did not rot. These samples did not rot at all. So it doesn't matter what Burkholderia cepacia you got. What it matters if you have a sulfur tolerance gene cluster in you or onion associated gene cluster in you. If you don't have it, you'll not be able to rot those onions. Now we have developed an assay to quantify if the Burkholderia cepacia has this gene cluster or not. So that will be included in our diagnostic. That's a good contribution for our diagnosticians, that they will not only able to tell you that this is you have a Burkholderia cepacia, they will be able to tell you if you have onion rotting Burkholderia cepacia or not. So moving forward. Pentoya. So Pentoya, I'm not going to talk about all the fundamental research, but I'm going to spend some time on the commercial varieties. If the commercial varieties have a level of resistance against Pentoya. So the way we screened our varieties. So what I'm going to show you the results of all the Vidalia lines and some of the lines from other non-Vidalias. The way we have inoculated or tested our lines. So what we did, we harvested the onion bulbs, graciously provided by Chris. From each onion bulb, we took the scale and we inoculated the onion scale with close to 10 to the power 8, close to of 10 maculated, which is 100,000 CFU coliforming units of Pentoya in the scales. And after 3 days, we wanted to see, we evaluated if these scales would form these lesions. The bulbs from where we got the scales, we also injected the good amount of bacteria in them and then assessed after 7 days. So the same bulb was inoculated, same bulbs, we took the scale, we inoculated the scale, and we also inoculated the bulb and tried to see, and then evaluated those. What you are seeing here, top 12 varieties that developed, that showed resistance to Pentoya based on scale assay, okay? Those varieties include Alba, Blanca, 10256, Rio del Sol, Chianti, Red Marvel, Maragogi, and so forth. Okay, these are good ones, top 12. And these are bottom 12s. The bottom 12s include Candy Joy, Amy, Sapphire, Matahari, Sweet Agent, and so forth. Okay, so these are the top 12 and bottom 12 based on the scale assay. All right. Let's look at the bulb rod based on the injection assay. When we injected the bulb, same bulb from which we got the scale, what are the things? We saw some of the variations in the resistance of the bulb rod with the variety which you are choosing. So these are the top 12 and the bottom 12s. The one which are in the which I labeled here are the one that showed resistance in scale as well as bulb. Okay, so first of the bottom line is that the scale resistance and the bulb resistance are two different things. Okay, so this is the one outcome of this research. Other thing which we found that there are only 3 varieties that developed that showed a displayed resistance on scale as well as in bulb, and they are Red Marvel, which is not a Vidalia variety, 10256.
Both of those other two are zero.
Zero, but
I don't know the commercial availability of those.
they are not yet commercialized as a Vidalia, but they are.
Well, they may be, I'm not sure. There's not a lot of them around.
Yep. And A1926, this one is also displayed both scale as well as bulb rot resistance. So don't run with this data. We are still evaluating those things and see this consistency of this research. Moving along, we also wanted to see if there is any resistance to Pentoya in our breeding lines or PI lines. So I was lucky enough to get a hand on a global collection, whatever lines was available in the globe, in alliums, to see if there is any resistance to Pentoya. So we collected close to 982 lines. We planted them in the field and as well as in the greenhouse. Close to 122,000 lines were planted. Long story short, out of 982, 981 lines were susceptible. There's only one line we found were highly resistant to Pentoya. All right. The second thing, we also looked at some of these bunching onions. You know, the onions that do not bulb. Most of the bunching onion varieties are naturally resistant to Pentoya. Okay. So we have bulb onions, but bulb onions, out of all 982 bulb onions, 981 were susceptible. But the bunching onions, the lines of bunching onions which we tested, most of them are either tolerant or resistant to Pentoya. But we are dealing with the bulb onions. I'm going to give you some of the examples here. This particular bulb onion, DPLD 1939, displayed a resistance response. What you're seeing here, control versus inoculated. This is a control, and this is inoculated, and we looked at the leaf lesion. So this is our susceptible check, sweet harvest. After 7 days of inoculation, entire leaf died away. This is our another susceptible check. Everything died away. But look at this one. This is the resistant response. You see some of these responses are because of natural senescence, but when we looked at the presence and absence of the bacteria in those senescence, we were not able to find the bacteria here, but we were able to find the bacteria over here. What you are seeing here, these are the bunching onions. Bunching onions do have a natural level of resistance to pentoya. When we further assessed the DPLD against our this resistant line against our susceptible line, we can see a clear difference. When we inoculate, you can see a significant reduction in lesion length, and these are the compared to sweet harvest with susceptible check, and these are our controls. Controls did not were not significantly different from each other. Look at this one. This is control versus inoculated of a resistant line. This is control versus inoculated of resistant line. You can see a little bit of lesion here, natural senescence with the control, and look at the complete dying death of the leaf here. This is how they produce a bulb. They're not a pretty looking bulb. This is how they will produce bulb in the greenhouse. So this is a sweet harvest, susceptible check. You can see all, I don't know if you're able to see, look at all the water soaking here. These are because of the movement of the bacterium from the foliage to the bulb, but DPLD, we did not see any of those lesions. And we further took these tissues, plated them on the plates. We found in 100% of the time, the bacteria was able to be detected from these bulbs, but none of the times we were able to detect the bacteria from the resistant lines. So DPLD 1939 is resistant to pentoya. All right. How much time do I have?
You've got 10 more minutes
10.
if you need it. And you can take longer if you need it.
Okay.
You're the last speaker.
Oh, I'm the last speaker. All right. So this is all about what I talked about, pentoya host resistance. I talked a little bit about Burkholderia. Now let's talk about Burkholderia and Cenerat together, how we can manage them together. In terms of products, one thing we found, all copper products work equally. Second thing we found, none of the copper products work on sour skin. Okay? Copper products work only on pentoya. Copper products will not have any efficacy on sour skin. What you're seeing here are the copper products. Look at the Cenerat. All the copper products were able to reduce the Cenerat, but none of them were able to reduce sour skin. Now, I'll throw a monkey wrench. There's one more thing which we found, that apart from the copper products, we also have LiveGuard, which is a software product, OMNI-listed product. This LiveGuard, over the period of last 4 or 5 years, we have seen that this LiveGuard has efficacy in reducing Cenerat, but not Cenerat. Well, it doesn't have efficacy in reducing, of course, Burkholderia or sour skin, but in Cenerat, it has a role to play. Whenever we used copper or LiveGuard in rotation or tank mix, it was able to reduce the Cenerat. Plus, LiveGuard by itself, if applied at a leaf senescence at a certain stage in a crop growth, it was able to reduce the Cenerat. So our growers are now rotating the copper with the LiveGuard. So LiveGuard can be rotated with copper products to reduce Cenerat severity. Okay, there's one more aspect to use of copper and LiveGuard, and I've shown you this one. If you have a thrips infestation, and we have shown that that Cenerat causing pathogen or pentoya are transmitted by thrips. If you do not do a good job in controlling thrips, none of the copper products will work either. So look at this one. This is a trial where we do not have any thrips, and this trial we had thrips, and this was done in the greenhouse so we can protect the plants against thrips. Look at Actigard, Coside, and everything, they worked when there are no thrips. Okay, we have a significantly reduced Cenerat incidence compared to the check, but the important thing, there are no thrips. But same treatments when you have a thrips infestation will not work at all. So all the copper products which I've shown, the Cenerat efficacy trial, all of these copper trials had a very strong thrips insecticide program. So what we are recommending, that do whatever you want to do, but you have to overlay your bactericide program, or copper-based program, or LiveGuard-based rotation program on top of the thrips insecticide program. This trial was done by a group of agents where we looked at bulb rot, Cenerat bulb rot, under no thrips control versus thrips control. And you can see with all these products, they had same level. If you have a thrips control, same product have enhanced efficacy when it has a thrips control versus no thrips control. For example, look at co-side. With thrips control, always had a better reduce bulb rot incidence compared to when there is no thrips control, and so forth. Even thrips control by itself looks better. If you just spray, if you do not do anything, but just do thrips control, it will by itself reduce center rot incidence. That's a long story short. Thrips program should be overlaid with the back reset program. So how do these findings make a difference in growers' behavior? First thing, growers have started using Lifeguard as a rotation partner with copper. Second thing, growers are also using thrips-based program. They're not relying a lot on the thresholds, but they're trying to see that they are heavily invested in providing thrips-based program and overlaying it with the back reset programs. All right, what's new? What's new in Burkholderia research? So some of the work done by Dr. Fande about a new product. The new product already got a registration. It's an Omni-listed product. So I'll give you a small background. Back when I was a postdoc, I worked with Dr. Langston and Dr. Ron Gitatis. We did a trial we did a fumigation trial in a heavily infested Burkholderia field in Tifton, where we used methyl bromide, we used Telone, we used whatever fumigant available in the market to reduce Burkholderia population. What we found, Burkholderia, or sour skin causing pathogen, was able to metabolize methyl bromide. Okay, it's the harshest chemical you can use, and it was able to metabolize methyl bromide. And in fact, Burkholderia population increased when we applied methyl bromide compared to when we did not apply. So you're looking at a highly recalcitrant pathogen, and none of these fumigants work. So this is a novel soil biofumigant. It came from, it's a plant-based product. When CAFUS looked at the efficacy of this particular biocontrol, soil biofumigant in a microplate assay, and he found that at a concentration above 0.25 and above, it was able to kill all Burkholderia, different Burkholderia species. He looked at Cepacia, Cynocepacia, Ambiferia, and some other Burkholderia species. So these are the population counts on the plates for different Burkholderia species. You can see this is a control. Okay, we have close to 10 to the 6 CFU counts. Co-side by itself, as I mentioned before, copper doesn't work on Burkholderia, and even different species of Burkholderia, copper did not make any difference. But look at this one, this product. This product above 2.25% and above, it was able to kill and reduce the population of different Burkholderia species, including Cepacia, Cynocepacias, Gliodioli, and Vietnamensis. So this is only first ray of light I could see on Burkholderia management, where you can potentially reduce the population in the soil. So next story is, what does it mean in terms of reduction of sour skin? So what he did, he conducted replicated greenhouse trials where he inoculated the soil with a high level of Burkholderia. They are heavily infested, okay? And then he came back with a product. The product is either at 0.125% or 0.25% or 0.4%. So he fumigated, biofumigated these products, this soil with that product. And then after a day or 3 of biofumigation, he planted these bulbs. These bulbs were already injured at the base of the plant, base of the scale. So what you're seeing, again, a soil infected or inoculated with the Burkholderia, followed by biofumigated with a different level of biofumigant, and then onions, which are already injured at the base, were placed on it. So let's see what happened to the controls. So this is the control. Control means onions, not biofumigated, but placed in inoculated soil. We could see good bit of disease here. Close to 100% of the bulbs were infected. Let's look at this one, 0.4%. When you have a 0.4% of the product biofumigated in that particular soil, the disease incidence was significantly reduced from 100% to close to 35%. It's not immune, but you can see a sharp decrease. Other percentages did not do a great job in terms of disease reduction, but did a good job in reducing some of the inoculum in the soil. I will talk about this later, but I want to show you this one. At 0.4% product, biofumigant product, the disease incidence was significantly reduced. Now, what you're seeing here, look at the above graph. This is a Burkholderia population before and after soil biofumigant. Okay, look at the control. Control did not make any difference. So we had a close to 100,000 cells, and even after and we used a PBS, and there's no difference. But at 0.125 and 0.25%, there's a slight reduction of the population. You'll see 1 or 2 log order reduction of the population at 0.125 or 0.25. But with the 0.4%, which is effective here too, the reduction of the population was tracking from 10 to the power 5 to 10 to the power 2. It is 3 to 4 log order reduction. It means 10,000 to 100,000 time reduction. So that was reflected in the reduced bulb incidence over here. So right now we are conducting a field trial with this product and see if this holds true in the field. But we do have a good greenhouse data, and these are replicated and shows a similar trend that at 0.4% of this product, we were able to significantly reduce the population of the Burkholderia, but also the phenotype, the sour skin in the soil, in the bulb. How much time do you have?
Well, you're out of time, but you're the last speaker, and this is the last meeting in this room. So
Okay.
we can go longer if we need.
It's up to you guys if you want to go long. Yes, Cliff.
Question, Professor. Pots, if y'all put the inoculated soil with disease, on that trial, y'all carry all that potted dirt, let the plant farm put on?
Do you want to spread it around the plant farm? You can blame it on Cliff, Omar. No, what we do with those, we are a very good steward of the environment. What we do, once we do these kind of trials, we autoclave all our pots as well as our soil. So,
I do have a question about that product.
yeah.
So the name of the product is Aster?
They have not commercialized the name.
Okay.
They just received the Omri.
So is not commercially available yet?
And one thing I would say, I'm not recommending this product yet. Let me do a couple of years of field assessments, and probably I'll do some assessment in growers field too. Once I see the consistency and the performance, then only I think we can go forward. But I could see a ray of light with this product.
Does it have to be soil applied, or can it before planting, or can it be applied over the crop?
Before planting. But there's we have one of the treatments where we're envisioning to use over the top, but probably it's gonna be next year. But this year we are doing pre-plant. Okay. Yes.
So for the 0.4%, that concentration, how long can it how long is the effect on the reduction?
That's a very good question. What is the residual effect? We have not tested it yet. All the assessments were done. Kefas, you can correct me. It was 3 or 5 days after application, or 7 days after application. When was all the assessments were done? The population assessments? 2 weeks after 14 days. At least after it has a residual for 2 weeks. Okay. All right, let's move on. So do culture. The question is, now the results which I'm going to show it's a combination of results of sour skin and center rot. We are talking about internal bulb rot. Our growers can grade out anything which is external. Okay, if you see the external bulb rot, they'll be graded out. Whatever I'm going to talk today are internal bulb rot, which are very hard to grade them out. So do culture practices affect internal bulb rot? And I'll show you some of the examples how culture practice would matter. So what you're looking at on the left is the mature onions. This is how we say the onions are mature. When the necks should fall over and bend naturally. It occurs because of the complete drying or partial drying of the neck. Sometimes if the neck is upright or neck is partially upright, they're not fully mature. Okay, they're not they have not reached the harvest maturity. And our goal is to harvest the crop as close to the harvest maturity because it impacts the storability of the onions and internal bulb rot. So this is what I'm saying. This is not yet mature, and this is harvest maturity here. So field curing. So just after the harvest, our crops are field cured for 48 hours. Some growers do 5 days, some growers do 7 days, some growers do 14 days. But more or less what we do is 3 to 5 days of field curing. The idea is to dry the neck as high as possible. After drying, we clip the onions. So Vidalia onions, 95% of our onions are clipped manually. We utilize our H2O workers to clip onions. And only 5% is mechanically harvested. So Chris, as a part of a USD and IFA project, he looked at the efficacy, or he looked at the internal and external bulb rot when onions are clipped manually versus using machine harvest. So our hypothesis, since we're using machine, the machine will cause more damage to onions. As a result, we have more internal rot in onions with machine harvest compared to manual harvest. But it was not true. It was not true. For 2 consecutive years, we have seen manual harvest had more rots compared to machine harvest. And it actually opened our eyes why we are seeing that. When we looked closer, what we seeing that high variability of onion necks when they are manually harvested. So this is an example of onion being harvested manually, and you can see how close it is to the shoulder. What do you think would be the fate of this onion in storage for next 2 months? They will rot internally. Okay? But look at this. This is the bulb after mechanical harvest. Mechanical harvesting resulted in optimized neck length. It leaves certain neck length throughout all the bulbs, in most of the bulbs. And as a result, what we hypothesize that because of this dry neck, longer neck, the pathogen over here will take longer or will not be able to get into the bulbs. Whereas pathogen over here will get into the bulbs much easier here. Okay. So neck clip closer to the shoulder, decreased storability and cause more internal bulb rot. Now question is, what is the optimized neck length? What length is the optimum that will reduce the bulb rot? You know that we have to have a dried neck, but we do not know how long the neck should be clipped so that we have a lesser bulb rot. So Ross Green, our county extension agent, and he worked with us and he looked at the optimization of neck length. He looked at either 1 inch length, 2 inches length, or 3 inches neck length. And what he found repeatedly, that if you clip the neck at 2 inches above, you have a significantly less or lower internal bulb rot compared to 1 inch or low. So for example, look at necks clipped at 1 inch or right at the shoulder had more internal rot, although the numbers are very low, but these numbers are much higher than these numbers, and this is consistent. Consistently, if you keep the neck, the first thing is your neck has to be dry, and second thing, it has to be clipped close to 2 inches or above. So don't blame me if you see, now you go ahead and notice that if you buy onion bags, look at their necks. Most of the necks are longer now. Even not only Vidalia onions, look at the red onions, yellows and whites and whatever. This information has gone viral. So everybody, all the growers have seen the benefit of a longer neck. But the thing is, if the neck, the subsequent question which we asked, the neck is supposed to be dry. But what drying means? What moisture content we should say the neck is dry? Okay, if neck is completely dry, it doesn't matter how you clip. But if neck is partially dry, then neck length matters. That's what we want to do. We wanted to assess further. Overall, all this work, this and that, will not be possible with the help of our county agents, our excellent cooperator, Mr. Chris Tyson, our excellent group of growers, and my lab members. So with that, I'd like to conclude my talk, and thank you. Thank you for listening. It's been a long talk. So, any questions for me? Yes.
All these, Good job. Thank you very much for your presentation. All these diseases you talked about, do you have them in tropical areas?
Center rot and sour skin are the top most bacterial diseases worldwide. We see most internal rots because of sour skin and some with the center rot. Okay. In other areas of the world, when we did the survey, first of all, they don't have a good diagnostic facilities. They do not know what they're dealing with. But some of the things we have seen is mainly sour skin caused by Burkholderia. So whatever impact we make here in southern Georgia will have an impact worldwide.
Any more questions?
Yes.
You mentioned botrytis, leaf blight, and just curious what the monitoring for fungicide resistance looks like, since botrytis is a high-risk pathogen.
Thank you. So we do a fungicide sensitivity test, but not in vitro. We do fungicide sensitivity in the field to see the efficacy of individual fungicides which are already labeled on onions every year and try to see how they perform. Over the last 2 or 3 years, I have shown that Scala, which is pyrimethanol, and your Merivon, which is another premix, have stopped working on botrytis. We have a resistance. The bad thing with botrytis is that when you try to isolate the botrytis and try to do in vitro assays, it's very, very hard to isolate botrytis. What we have seen, whenever we try to isolate botrytis, we get stem phyllium, because stem phyllium and botrytis coexist. When you have a botrytis infection, after a week or 5 days, you'll have a stem phyllium. And stem phyllium is a much fast-growing fungal organism compared to botrytis. So doing in vitro fungicide sensitivity assay with botrytis, nobody is able to do it yet. Any onion pathology, very, very hard. You have to do it in the field. Any more comments?
One question. When you were talking about Ridamil earlier for the Downy, undoubtedly the Ridamil piece is what's bringing that to the table. So it doesn't matter if it's copper, Bravo, or what? It doesn't. Okay.
So I just want to make it clear, since I just use Ridamil Gold Bravo in my trial, it doesn't mean other Ridamils are not working. The major heavy lifter in onion downy mildew efficacy is actually Ridamil. But you can use a copper, you can use a Bravo, whatever premix you want to use, you can use it. Any more questions? Chris?
Thank you, Bhavesh. Appreciate your talk today. That concludes the onion session. Thank y'all for coming today.